For decades, the dream of multiplanetary human presence remained largely aspirational. Now, a singular vehicle stands at the forefront of transforming that vision into reality: SpaceX's Starship. The 10th Integrated Flight Test, or IFT-10, represented a critical juncture in this ambitious endeavor. Each launch, engineers have stated, is not merely a spectacle, but a meticulously planned experiment, designed to push the boundaries of rocket technology and gather invaluable data for future deep space missions. This relentless pursuit of reusability and scale defines the Starship program's revolutionary approach. The Starship system comprises two primary components: the Super Heavy booster and the Starship upper stage. The Super Heavy, designed for initial liftoff, is powered by an array of Raptor engines, varying in number across different prototypes. Its purpose is to propel the Starship out of Earth's dense atmosphere. The Starship, equipped with its own set of Raptor engines, then continues the journey to orbit, or beyond. The stated design principle, according to SpaceX, is full and rapid reusability for both stages, a feat unprecedented in orbital-class rocketry, and a fundamental requirement for affordable space exploration. SpaceX has consistently described its Starship development as an iterative process, characterized by a build, test, learn philosophy. Each flight test, regardless of its immediate outcome, is considered a success if it yields critical engineering data. Analysts note this approach allows for rapid prototyping and design modifications, accelerating development cycles compared to traditional aerospace programs. Earlier tests focused on atmospheric maneuvers and belly flop landings, while more recent flights, leading up to IFT-10, escalated the complexity to include orbital or near-orbital profiles. This strategy, as stated by the company, is foundational to overcoming the immense technical hurdles. While specific details of IFT-10's trajectory and payload are not always publicly disclosed in full, analysts anticipated several key objectives. These typically include validating critical flight phases, the synchronous ignition of multiple Raptor engines, the precise hot staging maneuver where the upper stage ignites before separating from the booster, and the integrity of the Starship during re-entry into Earth's atmosphere. Furthermore, the Super Heavy booster's propulsive landing and the Starship's controlled splashdown at a designated target area were likely primary data points. Each element represents a significant engineering challenge. Before any Starship flight test, rigorous regulatory oversight is mandatory. The Federal Aviation Administration, or FAA, grants launch licenses based on safety, environmental impact, and public risk assessments. For IFT-10, as with prior flights, SpaceX submitted extensive documentation detailing flight profiles, potential debris fields, and emergency procedures. This process, often lengthy, underscores the complexities of operating such a powerful vehicle. Sources within the aerospace community highlight the critical balance between enabling rapid development and ensuring public safety, a constant point of discussion for any launch operator. A Starship launch is a multi-stage event, each phase carrying inherent risks and engineering challenges. From the moment of liftoff, observers scrutinize the performance of the Raptor engines. Super Heavy's boost back and landing burn demand precise control and timing. The hot staging maneuver, where Starship ignites while still connected to the booster, has been a particular focus for its innovative, yet complex, execution. And Starship's re-entry, particularly its thermal protection system, faces extreme stresses. Each segment of the flight provides opportunities for learning, but also moments of intense tension for the teams involved and the viewing public. Ultimately, the immediate visual outcome of a Starship flight test is only one dimension of its success. SpaceX's primary objective, according to company statements, is the collection of flight data. Thousands of sensors on board both Super Heavy and Starship transmit information on propulsion, aerodynamics, structural loads, and thermal performance. This telemetry, whether the vehicle lands successfully or experiences an anomaly, provides engineers with crucial insights. The analysis of this data then informs subsequent design iterations and modifications, forming a direct feedback loop that drives the development process forward. The 10th flight test for Starship contributes to a larger narrative, the pursuit of full reusability for orbital-class rockets. Historical context reveals that expendable rockets have dominated spaceflight, driving up costs significantly. SpaceX's Falcon 9, with its reusable first stage, proved the economic viability of partial reusability. Starship aims to extend this to both stages, along with in-space refueling capabilities. Analysts suggest that achieving this level of reusability could reduce launch costs by orders of magnitude, making routine, large-scale space operations, including extensive lunar bases and Mars colonization, economically feasible for the first time. The implications of a fully operational Starship extend far beyond Earth's orbit. SpaceX's long-term vision, repeatedly articulated by its founder, is the establishment of a self-sustaining human settlement on Mars. Starship is designed to be the primary transport vehicle for both cargo and crew to the Red Planet. Furthermore, it is central to NASA's Artemis program, designated as the human landing system for future lunar missions, aiming to return astronauts to the Moon. IFT-10, as part of this ongoing development, stands as a tangible step toward these monumental goals, marking progress on humanity's journey among the stars.